Hello everyone. Today we're going to be learning how to calculate the enthalpies of a reaction by using a table that has the enthalpies of formations listed. As you saw before, elements, the delta H's of formations are on a table in your appendix in your textbook. If you look at what we're going to be doing, we're going to be using those values so that we can calculate the delta H of a reaction using this formula right over here. If we look here, this will be the formula we'll be using. One note to make is that the delta H of formation for elements, and that includes diatomics, is 0. So you'll notice, let's say sodium or iron or a diatomic such as oxygen gas, the delta H of formation value is 0. A lot of times, they won't even give you that value. They'll assume that you know it's 0. Now, here's how this works. To find the delta H of the reaction, it's going to be the sum of the products minus the sum of the reactants. And you need to account the coefficients in the equation because it is dependent on how many moles you have. So you need to pay attention to that and multiply by the coefficients so that you adjust the number appropriately. If you look here, our first problem comes from the packet. And what we're doing is we want to find the enthalpy of the reaction when we combust propane according to this calculation or this chemical reaction that you see here. And notice the value of oxygen isn't even given because they are assuming that you know it's 0. However, we have the value of propane at 184.9. We also have the other values listed here. Carbon dioxide at negative 393.5. Okay? And we also have water at negative 285.8. So what you got to do here is to find the delta H of the reaction, you're going to get the sum of the products. The two products are CO2 and water. Let me rewrite that here. CO2, which you need to take into account that you have 3 CO2. So you got to multiply the number to negative 393.5. You got to multiply that by 3. And then you're going to add it to the other product, which is water. And that would be, notice there are 2 waters. Okay, so you got to multiply that. Well, let me fix this here. Got to multiply that by 2, negative 285.8. And then you're going to get, that's the sum of the products minus the sum of the reactants. Now, there's only 1 mole of propane, so it's just 184.9 plus. There are technically 4 oxygens, but you'll notice that 0 is the value. Therefore, that's not even going to matter. Okay, so once you have that set up, then you're going to need your calculator. You're going to get negative 393.5 times 3, and then that's going to be negative 1180.5. And then you got to multiply the other number here, 2 times negative 285.8, and that's going to give you negative 571.6. We're going to need to add these two numbers together, so negative 1180.5 plus negative 571.6 will give you, hang on one second here as I plug this in, you get negative 1752.1, and then it's going to be minus just 184.9 because this part over here is 0. So let's do that. So it'll be minus 184.9, and we get an answer of negative 1,937, and it's kilojoules per mole. And that'll be the answer to the first problem. Okay, let's go to the next problem. Now this one, also in the packet, is a combination of what we just did with a thermochemical equation, okay? First of all, you'll notice the values are given. Notice that iron is not given at all. That value is 0 here. And what we're going to do is let's go ahead and set up and find the delta H of this reaction. Okay, so let's see what this is going to be. So what we're going to do here is we're going to get the sum of the two products. There is 3 CO2s. Each CO2 is negative 393.5. And we're going to add that to the, if you notice, this won't make a difference. There's 2 irons there. So you know that part's just going to be 0. So it'll be the sum of the products minus the sum of the 2 reactants. Now there's only one Fe2O3, so that value is negative 824.2 plus there are 3 carbon monoxide, so we got to multiply that by negative 110.5. Okay, now we have that set up, so let's go ahead and do the math here. So the first thing we got to do is 3 times negative 393.5, and that's going to be negative 1180.5, and this part's 0, so we got that part already. Now let's see what this other part is. We got to first, let's do this part here. 3 times negative 110.5, that's going to give me negative 331.5, and then I'm going to need to add that to the negative 824.2, and then the entire part of the reactant side is negative 1155.7. And now what we're going to do is let's go ahead and add those two numbers up. So you got negative 1180.5. Really, minus a negative is just like saying you're adding 1155.7. And you end up getting negative 24.8 kilojoules per mole. What the packet did is they just rounded it to 25. Okay, you could leave it at negative 24.8. We'll go ahead and use 25. So if we round that, we got 25 kilojoules per mole. Now, this is the enthalpy for the reaction, but the question wants how much energy would be absorbed or released if we had 30, and let me put my negative here, 30 moles of solid iron. Okay, so we're going to focus on iron. And I'm going to erase a couple of things over here. Okay, so we're focusing on iron. And if you notice, it's negative, which means that energy is being released. So here's what we got to do. This now becomes a thermochemical equation. According to this equation, okay, we want to convert, we have 30 moles of iron, and it's 2 significant digits. Let me put a little dot there. So it's 30 moles of Fe. According to the equation, if you look here, and you want to set this up so units cancel, for every 2 moles of Fe, we just calculated that you released negative 25 kilojoules of energy. So what's going to happen is we're going to multiply the 30 times 25, negative 25 to be exact. And then when you divide that by 2, you're going to get negative 375 kilojoules. Now, if you round that to 2 significant digits, we could just call it, negative 380 kilojoules. So that would be the answer that we get in significant digits. So this problem is a combination of finding the enthalpy for the reaction, which was negative 25, and then using that to do a thermochemical equation to find out how much energy would be released in this case if we had 30 moles of solid iron. Okay, let's continue with the next problem. This one comes from the PowerPoint, and what they want us to find is the delta H for the reaction. Now the values are given here on the next page. These values can be found from the appendix in the book, and what I'm going to do is I'm going to go ahead, so we don't have to be flipping back and forth. I'm going to go ahead and place these values here. For ammonia, the value is negative 45.9. Oxygen is 0 because it's an element, as we mentioned earlier. NO, nitrous oxide, is 91.3. And notice that water is a gas. It's negative 241.8. These are the values on the next page. So let's apply what we learned. To find the delta H of this reaction, what you do is, let's get the sum of the two products. Okay, now there are 4 NOs, so we got to multiply 91.3 times 4. Okay, and then we got to add that to the 6 waters, so it's negative 241.8 times 6. And that'll be the sum of the products minus the 2 reactants. There are 4 NH3, so we got to multiply that by 4. That's 45.9. And then we got to add it to, this is going to be a mute point. There's 5 oxygens, but oxygen, that part's going to be 0. So let's do the math again. The setup is correct. So you go 91.3 times 4, and you get 365.2 plus, let's do this part here, 6 times negative 241.8, and that gives you negative 1450.8. And then this other part over here, well, we just got to multiply 4 times 45.9, okay, and that'll give us the entire bracket over here, 183.6. Okay, so let's add the sum of the two products first. So 365.2 plus negative 1450.8. This part is 1085.6, and then we'll subtract it here, minus 183.6, and we get negative 1269.2. Okay, and let's see if, let me check my math here. Oh, I made a mistake here. I just noticed something. Give me a minute. I'm going to fix this. There's a negative over here. So let me fix this part here. My apologies. Let me just fix this little piece right back here. This should be negative 45.9. So let me go ahead and recalculate that, and we'll get this piece here. So 4 times negative 45.9 is just a negative, let me write that down here, negative 183.6. Okay, so we got, this will end up becoming plus 183.6. So let me go ahead and redo this. Negative 1085.6 plus 183.6, and we get, now we got it, negative 902 kilojoules per mole. Well, you saw what just happened to me. You got to be very careful not to forget your negatives. Okay, so notice I forgot to put the negative over here. Luckily, it was a quick fix. Okay, let's move on to the next example. Okay, so this was the data from the previous example. So here we have another equation. It's highly exothermic according to the question. And what we'll do is we'll go to the appendix to get the values. Okay, the value for aluminum oxide from the appendix in your book is negative 1669.8 kilojoules per mole. Okay, now remember, aluminum and iron are both going to be 0 because they are elements. Okay, so then that means we got to look for one more. Let's look for Fe2O3 as a solid. And Fe2O3 has a value of negative 822.16. Okay? So now that we have the values, let's go ahead and set this up and find the delta H for this reaction. Well, let's do the sum of the two products. So we got only one aluminum, so it's 1669.8. Plus the two irons, which is 0, this part is gone, minus the sum of the two products, which would be negative 822.16, which would be, there's only one Fe2O3, plus the two aluminums, which are also 0. Okay, so mathematically this one shouldn't be too complex. The answer is going to be negative 1669.8, and then this basically becomes plus 822.16, and we get a delta H for the reaction of negative 847.64 kilojoules per mole. Okay, moving on to the next problem. This one is another combination of finding the enthalpy of the reaction and combining it with a thermochemical equation. So what we're going to end up having to do here is, this is how much energy is being utilized per day. The goal is to start with this number, with the energy, okay? And then we're going to have to convert it to moles by using the conversion factor from the equation, and then going to mass. Now over here, when we go to mass, this will probably be in grams. So according to this, they do want the answer in kilograms, so we'll probably have to do an extra step. Okay, and that will be to convert from grams to kilograms. So on the next page here, you'll notice that the first step, and this one's worked out for us, the first step is, it is the combustion of octane. Okay, octane has this formula right over here, and combustion always means you're reacting it with oxygen and you're making carbon dioxide and water. This was balanced using a fraction, but you can also write it like this. You can put C2 or 2C8 like that, H8, plus 25 oxygens, okay, just like that, yields 16 CO2s and 18 waters. You could do it this way if you want to avoid fractions. The solution that is mapped out here, if you notice, the values are given. Notice oxygen is 0, and they use the formula. All right, they put the sum of the two products. So what they did was, and I'll go ahead and use the one that's given here. They got here for the products. Okay, there's 8 CO2s, so they multiplied 8 by the value of CO2, which is right over here. And then they multiplied 9 by the value of water, which is right over here as a gas. Okay, and then they added that up and got this number that you see over here. Then they also did the same thing with the reactants. Okay, the two reactants is octane, and here is the value. As you can see, the value of octane is negative 250.1, which is right over here, times 1. And then they used 25 over 2, which is really 12.5. So they got it's times 0. So this is a moot point. That's going to be 0 anyways. So when you do the products right over here, the sum of the products minus the sum of the reactants, you get this as your delta H for formation. Now we're not done. We're gonna use that now for the next step. Okay? On the next step, and here's how you set it up, is you were given, this is how much energy, because we're gonna go from energy to moles. And you use the conversion factor from the equation. If you recall, for every 1 mole of octane, this is how much energy is being released. That's what we just calculated just a moment ago. So the kilojoules are going to cancel, okay? And then you're going to be left with mass in grams. And then the final step is to go from grams to kilograms. As you can see right over here, you're going to end up dividing by 1,000. And once you divide by 1,000, since everything here has 2 significant digits, the original question has 2 significant digits, they rounded it to 2 and they got 2.3 times 10 to the 6 kilograms of octane. So this is how you do this one. Now this one's worked out for you, okay? We're going to do one together now that's going to be similar, where we're going to find first the delta H for the reaction, and then we'll do a thermochemical equation. Okay, so let's conclude with this problem here. If you look at the equation, all right, the only thing we're really missing here, iron, the delta H is 0, it's an element. So is oxygen, it's 0. And we actually worked with this one a little while ago. Fe2O3 from the appendix is negative 822, okay, 0.16 kilojoules per mole. Okay, so if we set this up, let's find the delta H first for this reaction. So what you do is you get the delta H of the reaction is equal to the sum of the products. Now there's only one product, okay, and we're going to have to multiply it by 2 because there's 2 of them, minus the sum of the 2 reactants. Here's the nice thing about this one. The math is going to be pretty easy, because this entire side is going to basically be 0. So when you get your calculator and you multiply 2 times negative 822.16, you get negative 1644.32 kilojoules per mole. This is the delta H of the reaction. Now, that's the answer to the first part. They also want you to do this. We have a reaction, and they want to know how much heat a hand warmer containing 15 grams of iron powder would be produced. So the focus here, and I'm going to erase these numbers. We don't need this right now. The focus now is going to be on Fe, on iron. What we're going to do is we're going to convert, and here's the steps, the mass of iron into moles of iron, and then we're going to use the conversion factor from the equation to find the energy released by the iron. So, first things first, we need to convert the mass of iron into moles. So we're going to have to divide by the molar mass of Fe. Okay, so let's set that up. So we got 15 grams. If we divide that by 55.85 grams per mole, the G's are going to cancel. Let's find out how many moles we have. So 15 divided by 55.85 gives us 0.2685, and there's more numbers. I'll just round this to an 8. It's 576. I'll round it to 8, and that's moles of Fe. Now we're going to go from moles of Fe to energy. If you look at the equation, the conversion factor says, and focus on iron here, okay? For every 4 moles of Fe, we calculated that we're going to use 1,000 or release 1644.32 kilojoules of energy. That will allow our moles to cancel. So when you get your calculator, multiply the moles of iron. Okay, first multiply by negative 1644.32. And then don't forget to divide by 4. And let me write the answer on the top of the page here. The answer that I get is negative 110. I'll round it to 0.41. Okay, kilojoules. If you want to use significant digits, since there are 3 in the question, we could just put negative 110 and put a dot there, and that should be fine. Okay, that's how much kilojoules is going to be released, negative 110 kilojoules. So this type of problem, they like to ask that on AP Chemistry. They like to combine finding the enthalpy of the reaction by using the data and using the equation, the sum of the products minus the sum of the reactants, and then afterwards combining that with a thermochemical equation, which is what we did here at the end. Okay, now make one note. A lot of times they're not going to give you the values of elements or diatomics, the delta H of formation values. They're going to assume that you know that those values are 0. So if you feel like you don't have enough information, it's because they're assuming that you know that those have a 0 value. The others they would give you. Okay? I hope this helps, and that will conclude today's lesson.